Alright guys, for this one, I started by just getting a little setup here so that we don't have to waste too much time watching me draw. But for this one, we want to try to sketch the graph of something called the four-leaf rose, which is given in polar coordinates by this equation, r equals cosine of 2 theta. Now, the idea here is that the radius r is going to depend on the angle theta. So one way that we can try to get a picture of this is we can plot a few points and then just think about what's going to happen after we've plotted those points. So let's just start by plugging in. I listed out some angles over here, theta, to plug in. And so if we plug in r equals 0, then this one, if theta equals 0, then the radius becomes cosine of 0, which of course is equal to 1. So let's over here say that that's 1. Of course, the usual x-axis corresponds to the angle theta equals 0. Okay, now we go up to theta equals pi over 12, and so for this one, this is equal to the output of cosine of pi over 6, because we have to double the angle. And that's, of course, root 3 over 2. Root 3 over 2 is a little smaller than 1. And so we go out this ray, theta equals pi over 12, but we go out root 3 over 2 units instead of a 1 full unit. All right, we continue this process. So when theta equals pi over 8, we plug in to the cosine, have to double it. It becomes cosine of pi over 4. That's root 2 over 2. And so these angles, as we plug them in, the next one, it doubles, becomes cosine pi over 3. That's a half. Right? And then very quickly, when we get to cosine pi over 4, something interesting happens. Because when we double pi over 4, we get pi over 2. And cosine of pi over 2 is 0. So if the radius is 0, there's only one point in the plane that could be. It has to come back to the pole. Okay? And so just between 0 and pi over 4, this is corresponding to this ray, pi over 4, even though it doesn't go out the ray, it goes out 0 units for the radius. But just between the angles 0 and pi over 4, we've started out here and came all the way back to the origin, or the pole in polar coordinates. So the next thing we want to do is plug in this angle pi over 3. Well, what happens now? This becomes cosine of 2 pi over 3, because we have to double the angles. And 2 pi over 3 is actually the angle which lives over here in quadrant 2. It's the reflection of this angle pi over 3. Okay? And so cosine over here of 2 pi over 3 is actually negative 1/2. Well, what does that mean, right? So if that's a negative 1/2, then what we have to do, we have to go out the angle pi over 3 that we started with, though, right? But we have to go out a negative amount of units. So actually our point sits over here in quadrant 3 now. All right, and so you can continue this process, and you should, and what you'll end up seeing is that this curve will trace out a shape that looks something like this. So it's traced this out between 0 and pi over 2, and then it kind of turns around, comes back up. It doesn't do that. Comes back around, it's just looping around, loop-de-loop-de-loop-de-loop-de-loop-de-loop. These are all supposed to be the same. They're all supposed to go through 1 on their major axes. And then it looks something like this. This is bad. All right, but that's the general shape, and this is called a four-leafed rose. So it traces out 4 equal leaves. These leaves don't look equal because I can't draw. But it traces out 4 equal leaves. And this is called the four-leafed rose. All right, the second part of this question is to try to write down an integral that will compute the area of one of the leaves. All right, we just saw that the way that the leaves are traced out is not maybe the most obvious thing. So let's start with the first leaf, which, by the way, if you plot this yourself, it looks more like this. Okay, this one wants to continue this way, right? We don't want it to. So what we can do actually, this, by the way, is kind of tangent to this angle of pi over 4 here. Actually, if we go into quadrant 4, and we look at the angle negative pi over 4, and we trace this out backwards, this will just pick up on this side, and this will fill out one leaf this way. So if we let our boundaries for theta go from negative pi over 4 to positive pi over 4, then our leaf will get traced out in exactly, by the rays, right? Exactly the way I'm shading this in right now. Okay? Now there's other choices we can make, but to make sure that we have one solid leaf and we want to write down an integral that gets the proper area, the area, of course, should be the double integral over this region of 1 dA. This always finds the area of the region that you're integrating over, and so our region D is this one leaf. All right, and based on this conversation here, we've got that our integral in the theta direction is, this is just bound by constants, so negative pi over 4 to pi over 4. And then the inner integral with respect to r, this is going to be enclosed by the function cosine of 2 theta in the upper bound, and in the lower bound it's just 0. Okay? And then 1. But then remember, we're taking an integral in polar coordinates, so we have to integrate 1 times r times dr d theta. Okay? And so this is the integral that you should compute now to get the answer to part C, which is the actual area enclosed by one leaf.